Hello everyone. Statistical analysis constitutes a vital aspect of most orthopedic papers in the present era of evidence-based medicine. In this talk, I will provide an overview of the subject and explain the choice of statistical techniques. The term statistic refers to the science of collecting, summarizing, and analyzing data, drawing conclusions from the scene, and presenting it amicably. It may be just descriptive or inferential. Descriptive statistics involve summarizing the data. It is usually not feasible to study a whole population. Rather, we select a representative sample out of it and use the data to tell us something about the population. This process is called inferential statistics. The two inferential processes are estimation of population parameters and hypothesis testing. However, it is important to note that the term statistic refers to the value which we calculate from the given data set, for example, sample mean and standard deviation. Corresponding values of the population are called parameters. For example, population mean mu and variance sigma square. The term data refers to the observations made on the variables of interest. The variable is either categorical, where each individual belongs to one of a number of distinct categories, or numerical, where the values may be discrete, for example, number of individuals, or continuous, for example, height, weight, BMI, Harris score, etc. The type of variable determines the form of data presentation as well as analysis techniques which are suitable. We display the frequency distribution of a categorical variable in a bar diagram in which separate bar is drawn for each category, or in a pie chart. We use a histogram for continuous variables divided into continuous classes. By looking at the shape, we can assess whether or not the distribution is symmetrical. With the statistical softwares, we can actually overlay a normal curve on it for better comparison. Categorical data is summarized by number and proportional percentage. For numerical data, we need a measure of central tendency and a measure of spread. For normal data, we use mean and standard deviation. However, if the data is skewed, the median is used as it is not unduly influenced by outliers. The range is the difference between the largest and the smallest observations and is heavily influenced by outliers and should be used cautiously. The interquartile range contains the central 50% of the ordered observations, that is the third quartile minus the first quartile. These are depicted as a box and whisker plot as is shown here. In normal distribution, the interval containing the central 95% of the observation is approximately equal to mean plus or minus 2 standard deviation. The distribution is called symmetrical when the left hand side is a mirror image of the right hand side, and here mean and median and mode all coincide. It is skewed to the right or positively skewed when there is a long tail towards the right side with few high values. Here mean is greater than the median, which is greater than the mode, and negatively skewed or left skewed when there is a long tail on the left hand side. Here mode is greater than the median, which is greater than the mean. Peakedness or kurtosis can also be visualized. It can be leptokurtic or high, mesokurtic or normal, or platykurtic or flat. The sample estimates of parameters may not coincide exactly with the true values in the population. We calculate a quantity called standard error of the mean, which is equal to standard deviation divided by the square root of sample size. The 95% confidence interval of the mean is the interval within which the true or population mean would lie 95% of the time. So if we repeat the sampling procedure infinitely many times, it is obtained by adding and subtracting two standard errors of the mean from the mean. Standard error of proportion is estimated as under root of p into 1 minus p by n, and its 95% confidence interval is also similarly derived. Hypothesis testing is an inferential procedure where we use our sample data to draw conclusions about the population. When we are evaluating a new treatment in comparison to the standard management, the null hypothesis H0 states that the two treatments are equal. We calculate a test statistic and relate it to the relevant theoretical statistical distribution, which will be normal, T or F or chi-square distribution, and obtain a p-value. The p-value is the probability of obtaining the sample values as extreme or more extreme than those observed if the null hypothesis is true. The p-value, like any probability, ranges from 0 to 1. If the p-value is sufficiently small, we reject the null hypothesis and call the test statistically significant. If it is large, we do not have evidence to reject H0. Level of significance is specified by us distinguishes between the large and small p-values. An arbitrary value of 0.05 is considered if it not gets rejected if we were the alternative hypothesis. Usually it is two-sided, which means that the population means or medians are not equal. One-sided alternative hypothesis is rarely used when one treatment is known to be superior. As such thought can itself be arbitrary, two-sided tests are far more superior. So a series of questions need to be answered to reach at a suitable test. Is the variable categorical or numerical? How many groups are being compared? Are the groups independent or are they paired or related? Are the assumptions underlying the test under consideration satisfied, in which case we can use parametric tests, and if not, we use alternative non-parametric or distribution-free tests. So if we have a binary categorical variable with two groups which are independent, we can use a chi-square or Fisher's exact test. If they are related, we can use a McNemar's test. If we have more than two groups which are independent, we use chi-square test. And if they are related, for example, time trend data, we use Cochrane's Q test. If we have a numerical variable with two groups which are independent, we use two sample t test if the data are normal. Otherwise, we use Wilcoxon rank sum test, also called as Mann-Whitney test. If they are related or paired, we use the pair t test. If the differences are normal, otherwise we use Wilcoxon sign rank test. If we have more than two groups which are independent, we use one-way ANOVA. If the assumptions like normality and homogeneity of variances is satisfied, otherwise we use statistical variance test. If they are related, for example, follow-up data, we use limited measures ANOVA. Assumptions like sphericity are satisfied, otherwise we use Friedman test. So two types of errors may be committed in hypothesis testing. Type 1 error refers to incorrectly rejecting the null hypothesis. And type 2 error refers to not rejecting the null hypothesis when it is false. The power of a test, the chance of rejecting the null hypothesis when it is false, that is 1 minus the type 2 error probability. We should have adequate power of more than 80%. If the power is low, then we may fail to reject a true effect as significant, and as this is wasteful of resources, such studies are unethical. A priori sample size estimation saves against this. Softwares like NMaster are available nowadays for this purpose. We plot a pair of values x and y, say height and weight, for each individual on the scatter diagram and visualize a straight line which passes amidst these points. Karl-Pearson correlation coefficient R is a measure of the linear relationship between the values. Its values range from -1 to +1, indicating direct or inverse relationship respectively, with 0 indicating no relation. For ordinal variables or non-normal relationships, we use Spearman rank correlation coefficient. We obtain a linear regression equation y is equal to a plus bx, by which the independent variable x will be used to predict the dependent variable y. The A estimates the intercept and B estimates the slope, which is also called as the regression coefficient, representing the mean change in y for a unit change in x. Softwares also provide us the p-value and the confidence interval. R square represents the proportion of the total variation explained by the relationship. Model assumptions are checked by analyzing the residuals, which refer to the difference between the observed values of the dependent variable y and its predicted value, and these should be normally distributed and have uniform variance. Multivariable linear model has a number of explanatory variables like x1, x2, etc. For example, mortality after hip surgery may depend upon age, sex, BMI, and comorbidities. The regression coefficient B1 represents the change in Y for unit change in X after adjusting for other covariates. For binary response variable, we perform logistic regression, where the explanatory variables are related linearly to the logistic transformation of the outcome probability, that is log of P upon 1 minus P. Regression coefficients in the model provide an assumption of the adjusted odds ratio for the predictor. If individuals are followed for different lengths of time, we use Poisson regression, assuming constant event rate. Cost proportional hazard regression gives the effect of each variable on hazard ratio in survival analysis, for example, in failure after hip arthroplasty. Kaplan-Meier survivor curve is a simple graphical method. The horizontal axis represents the time and the vertical axis represents the cumulative probability of survival. Non-parametric log-rank test is used to compare the two survival curves. Validity refers to the extent to which the tool really measures what it is supposed to measure, and reliability measures the reproducibility when the research is repeated under identical conditions. Validity will be classified as construct validity, that is correlation with tools measuring related concepts; content or phase validity, that is if it covers all the aspects of the concept based on expert opinion; and criterion related validity, that is the correlation with other known valid measures of the same thing. For example, correlation of head size on preoperative templating with the actual head size using hemiarthroplasty. For inter-observer reliability, the same observer may repeat the measurement after a period of time, and for inter-observer reliability, two observers may take the measurement in each patient. If the data are categorical, we use the Course-Biostatistics, which measures the proportion of times the observers agree, accounting for agreement by chance alone. Similarly, ICC is used for numerical data. In blind and independent approach, we plot the difference between each pair of observations on the vertical axis and their mean on the horizontal axis. The upper and lower limits are obtained by adding and subtracting 1.96 times the standard deviation to the mean. In any diagnostic study, we calculate the sensitivity and specificity and their confidence intervals. The clinicians are more interested in positive and negative predictive values. Bayesian approach uses test data to modify the prior probability reflected by the prevalence of the disease to estimate the posterior probability. Thank you.